So let's start. Last time we ended with the discussion of the golden bracket and of holonomics, and also in the end of Rui's lecture he mentioned holonomics. Let me just briefly recall what those, just to put the discussion on a firmer ground. Let me just a little bit recall what those holonomics are, because they're going to play an essential role in today's lecture. So, and then we also look a little bit again at the golden bracket. So let me recall the following notion. Suppose I have a one form on a 0-1 segment with values in the Lie algebra G. So then I want to define a holonomial of A for this segment. And in fact the idea is as follows. So there is a unique map G from this segment to the group, which solves the following problem. So G of 0 is a group unit, and so here you can write it either this way, G star of theta left, or as we used to do it, G minus 1 dg, and this is equal to this given one form A. So then, by definition, the holonomial is G of 1. Now recall what was going on with the surfaces. So we would draw a curve on the surface with some base point P. Well, I'm not sure whether my drawing, really represents something meaningful on this curve, but well, let's try to think about it. So now we have a curve, and this actually means that we have a map from 0-1 to sigma, let's say gamma. In fact, in this particular case, it's a closed curve, so this means gamma of 0 is equal to gamma of 1 and is equal to P. And, well, we assume that we have a flat connection on sigma. Well, then what we do, we simply pull it back to the 0-1 segment and then use this definition of the holonomial. So the holonomial so we just take the pullback gamma star of A. Well, what is nice about this situation when the connection is flat, then this holonomial up to conjugation only depends on the homotopy class of the path. So A flat. So up to conjugation only depends on the homotopy class of gamma. Okay, so let me recall this story with the golden bracket. So to holonomics we were assigning some functions, in fact, by using representations and traces, but at this point perhaps it is not that important. So for two curves, so let's say this is one curve and that's another curve. I'm a bit hesitant how it should go. So here are two intersection points. So for two curves, let's say alpha and beta, we assigned the Goldman bracket, and the feature of this Goldman bracket was that it was a sum over the intersection points between the curves. So then it was some sine and some w of a new curve. Well, in general, this is a complicated construction, but it has one simple feature. So if the intersection is empty, then the Goldman bracket is 0, right? So if there are no intersections, then, well, there is nothing to discuss. So from there we can draw an immediate and nice conclusion. So an application. Suppose we have a surface with a boundary. So this sigma is a circle. Well, then one curve that we can invent, that's a curve which just circles around the boundary. Maybe it's some distance of it, or you can also put it on the boundary. Let's say it's our alpha. Now, well, we can choose any other curve. Let's say this is beta. Of course, in general, beta and alpha may intersect. But as I said, in the case of flat connections, you're allowed to move your curves by the homotopy. Now, well, what should we do? Like, take this second curve and redraw it such that it no longer touches the curve which circles around the boundary. Well, this shows that the Goldman bracket of W alpha and W beta is 0, because we can redraw beta such that the intersection of alpha and beta becomes empty. Well, this actually means that W alpha is a Casimir function. Well, maybe here I rush a little bit. So I only prove it for functions defined by the Goldman, by this Goldman's construction. But in fact, it's true anyways. It's true in general. So this is an indication that W alpha might be a Casimir function, but actually it is a Casimir function. Well, anyways, let's return a little bit to the situation of the moduli space for a curve for a surface with a boundary. So remember that we have this construction M of sigma g is equal to the quotient of some bigger space. So this is in general an infinite dimensional space divided by the loop group. So just to recall you, that's the space of connections on our surface which are flat, but here we only divide by the gauge transformations which are equal to 1 on the boundary. So in fact we stated that this space is Poisson. Now one interesting question is, what are these symplectic leaves? So how can we turn it into a symplectic space? Well, now let me give you the answer. And in fact, it's a little bit indicated by the construction of the Goldman bracket that I showed to you here. So first of all, notice that there is a natural map from the space N into the space of connections on the circle. So we decided that the boundary component is just a circle, and this map is a restriction of A to this sigma. Well, since here the gauge transformations are forced to be equal to 1 at the boundary, this map is actually well defined. Those gauge transformations, they don't touch to this connection on the boundary, so it doesn't change. So the map is well defined. And here, well, there would be still LG acting by gauge transformations. So for simplicity we assume that G is simply connected in these discussions. Then later on I'll make some comments about the more general case. So then this space turns out to be isomorphic to the quotient of G by the action by conjugations. So which means that G is mapped to HG, H minus 1. Now, just to give an indication why this might be true. So, what will be the map from omega S1G to G? Well, this map is just what we described up there. Suppose I take an element here. So what I do, I'm just mapping it to the holonomy. I don't know, how do you want me to parameterize the circle from 0, 1 or from 0 to 2 pi? So there are different schools, but well, let me just say S1, but it's understood I have to choose the base point. Sorry, A S1. S1, so this will be an element in G. Now, so before the quotients are taken. Now, the choice of the base point is the action of conjugation, and what is important, and maybe here I should write this formula. So if you have a holonomy for the closed path starting at P, then the holonomy of the gauge transformed connection for the path gamma is a conjugation of the holonomy of A by the value of G at the base point. So that is both the choice of the base point and the gauge transformations. They only lead to a conjugation of the resultant element. So we have a well-defined map. So one still needs to show that it's really an isomorphism, but that's maybe I leave for a moment. Now, well, let's look at a little bit more at the structure of this space G mod G. So let's say G is compact, semi-simple. So then G mod G turns out to be the same as the quotient of the maximal torus by the action of the while group. Now, how does this quotient look like? Okay, let's look at two examples. So one example, let's say G is equal to SU2. So here, for instance, I can choose a maximal torus to consist of diagonal matrices, and then so the while group exchanges the two eigenvalues. So the while group is Z2 exchanging the two eigenvalues. Now, what is the quotient? Here, the torus is just a circle, and we take a quotient of this circle by this Z2 action. For instance, we can think that C mod W, we can model it as the segment from 0 to pi. So these are the values of phi. Right? So other values of phi, they will be you obtained by the action of Z2. So that's, for instance, one possible realization. So notice that the endpoints of this segment, they correspond to the unit matrix, and the other one corresponds to the matrix minus 1. That's where phi is equal to pi. And these are two central elements of SU2. Just to give you a glimpse into a more general picture, so let's say for G equal to SU3, so now I'm gonna draw the picture for the Lie algebra of the maximal torus of SU3. So this maximal torus is two-dimensional, so it's handy to introduce those lines. In particular, this will be the while chamber. So there is an exponential map which maps the Lie algebra to the torus. Now, well, of course, the origin maps to the group unit. And here somewhere, so you know that the center of SU3, it's Z3. So there is a group unit and two non-trivial central elements. So let me choose the preimages of those central elements. So those two map to central elements. Now it turns out that C mod W is now isomorphic to this triangle. So you see, you just take a triangle spanned by the preimages of three central elements, and so this is called the Weil alcove. And well, one possible notation is delta. Well, for all SUNs, this would always be a simplex with vertices being the preimages of the central elements. For other compact simple Lie groups, it's going to be more complicated. It's always going to be a simplex, but not all the vertices will be central elements or the preimages of central elements, just because there is not enough central elements in other in other compact semi-simple Lie groups. Okay, so we have this map, and it turns out that in order to choose symplectic leaves, we just need to choose so the symplectic leaves are just fibers under this map. So we have a map into the vial alcove, and so symplectic Moduli spaces. Like when first, to simplify things, let's say this sigma is S1, so then there will be a mu of m of sigma g, and then I'll choose an element. Let me call it mu. I'm not so sure. Mu, is it a good notation? Mu was the moment map, but I hope it wouldn't lead to too much of a contradiction. So this is an element of the alcove sitting in the Lie algebra of the torus, and by definition, what is it? So these are flat connections on sigma. Their curvature is equal to 0, and the holonomial of the connection around this sigma, let me write it and then I explain. So it is contained in the conjugacy class, right? We now look at up to conjugation. So it's contained in the conjugacy class of this particular element. So I take an element of T which is sitting somewhere inside this alcove, I map it to the torus, and then I can still allow for conjugations. So CH, by definition, is the set of conjugates of an element H in G, and well, here this exponential of mu, that's an element of the torus. So these are symplectic Moduli spaces when you have one boundary component. Well, perhaps let me also say how it's going to look like when you have many boundary components.
Can you repeat the definition of curly C?
Curly C, right. So you choose an element in your group, and you look at all the conjugates of this element with respect to the conjugation action by the group. So this is just an orbit of the conjugation, action. So we're gonna return to this discussion in some minutes. Right. Okay. So now what happens if you have many boundary components? So now this sigma. Sorry? Yeah, okay. That's true. I didn't quite prove it. That's let's admit. So now, what happens here? We know that this space is Poisson, right? So then we need to analyze what are these symplectic leaves. So where would we have non-degenerate forms? Now, one indication why this might be true is as follows. I show you that if you take the W's, the Goldman functions which correspond to the boundary loop. So those functions, we see they are Casimir functions. What are Goldman functions? Goldman functions are spectral invariants of the holonomy map. So we take a holonomy map, we take it in any representation, and we take a trace of it. Right? So this is a kind of sum of eigenvalues. We can take it in any representation. So basically this tells you that the information about the conjugacy class of the holonomy, so this will be Casimir functions. So at least you need to fix the conjugation class of the holonomy. In principle, of course, it could have been smaller. But it cannot be bigger after consider that. So basically, we know that the symplectic leaves are for sure contained in those sets. So they cannot be bigger than those sets. But it turns out that these are symplectic leaves. So in one direction we see it from those considerations. Okay. So what happens in the more general case? Well, then actually the story repeats itself, because you can play this trick that I did with a Goldman bracket on each component of the boundary. So there will be moduli spaces, mu sigma g, and then, well, you have to choose now k points in the alcove, and this will be a omega sigma g. The curvature is 0, and the holonomy around the ice component of the boundary is contained in sigma, in C of exponential of mu I. So, sorry, just a second. So this is the ice component.
Is k equal to the number of components?
Yeah, k is the number of k is the number of components. That's right. Okay. Very good. So now, actually, we have some kind of idea how we can construct those complicated moduli spaces. So we have an infinite dimensional description. We know, well, haven't quite proved it, but we know what are the symplectic leaves. So we have Poisson spaces, we have the symplectic leaves, which are symplectic spaces. Now, let me give you a finite dimensional description of those spaces. So in fact, we want to know in more details how those spaces look like. So, now the finite dimensional description. So again, let me assume for now that G is simply connected. Okay. So then, perhaps let me start with the situation.
Is G also still compact?
Sorry?
Is G also still compact?
Yeah, let's assume for simplicity that it is compact, even though some of the formal constructions certainly work in the non-compact case. What one would really worry about in the non-compact case, what kind of space one is getting in the end. So then maybe you need to fix some component of this space that you want to look at. Like, for instance, people look at elements of the, say, non-compact group being hyperbolic, or being like, there you fix some extra properties, mostly to ensure the nice features of the quotient. In what concerns the formal constructions and the formulas for symplectic forms, usually they are quite universal. So they work whatever you do. But then, of course, the topology, they don't quite know about the topology of what you're doing. Your space might become quite nasty in the end. Of course, if it is compact, then you have more control over the singularities that it develops. I'll say a little bit about the universality of the formulas in a due course. Okay, so it turns out that M sigma G is isomorphic to the space of representations of the fundamental group of sigma into G modular the action of G on the space by conjugation. Now, how does this map look like? Well, that's the moduli space of flat connections. Its points are classes of flat connections. So let's say we choose a class of such a connection. So let's choose, so we have our surface. So let's choose a base point. And now let's choose an element here, let's say alpha. We can realize this element as a curve which starts at P and which goes, well, which returns to P. Let's call it alpha hat, a representative. So then, this guy, this A, should be mapped to a homomorphism from pi 1 to G. Well, now I guess since we started this hour with a discussion of holonomies, you see that this map will be mapping alpha to the holonomy of A alpha hat. So that's the prescription. Well, of course, here we only have a class of A under gauge transformations, but we know that gauge transformations only lead to conjugation, and here we divide by conjugation. The same holds true for the base point. Again, we can choose another base point, but that would only lead to total conjugation of this space. So we have a map in one direction. Now, of course, we should still see why is it an isomorphism. Maybe I'll leave it as an exercise where you should use. So I constructed the map in one direction, right? To see that this is an isomorphism, it's probably good to try to see how to go in the other direction. And so the other direction uses G. Simply connected. I'll give you some indications in some minutes on how to do it. Right. So, but more concretely, this still sounds very theoretical. Let me say a bit more concretely. How do those spaces look like? Right. So first let's look at the case of sigma of genus G and no boundary. So in this case, pi 1 of sigma is a free group with generators A1B1 and so on, AGBG. So this corresponds to A and B cycles of the surface. And modulo 1 relation. So let me write it down. So the relation says that the product of group commutators is equal to 1. Here perhaps just to remind you that the group commutator by definition is Hg H minus 1 G minus 1. So in particular this means that M of sigma G, what is it? So this homomorphism, this map, is completely defined by the images of generators. So we need a 2G tuple of elements in G, and we need the relation to be satisfied. So the relation A1 commutated B1 and so on, AG commutated BG equal to the group unit, and then we should divide it by the action by conjugation. Now, some other example. So sigma is still of genus G, but this sigma is a circle. So now, well, if you allow, perhaps I would just correct a little bit here and then write it just, yeah, maybe I should have written it down there. So yeah, let me correct it here, because this would be faster. So here I replace it by S1. So then you add one more generator. So that's the generator which corresponds to this circle which goes around the boundary. And now you also add it in the relation. Now, of course, this means that you can express this generator in terms of those commutators. So this means you can forget the relation and forget the extra generator. So the fundamental group for this surface with one boundary component is just a free group with 2G generators. Well, so this means that for the moduli space of flat connections, we just forget the relation and get 2G copies of G and divided by the action of conjugations. So this is a Poisson space that we obtain. So it's G to the power 2G divided by G. Now, perhaps a bit more interestingly, what happens if in the same situation we want to look at the symplectic component, one of the symplectic leaves? Well, so again, there will be those 2G elements, and now, well, so the product of those group commutators, it should now live in the conjugacy class of the exponential of mu. And this is all divided by G. Well, maybe the last example, and then we discuss a little bit the properties of those symplectic and Poisson spaces. So the last example, let me take a sphere, so genus 0, with many, many boundary components. So we'll look at something of this sort. So G is equal to 0, and this sigma is a union of k copies. So now, well, what is pi1 of sigma? Well, for each boundary component, you have a generator, and then there is a relation that their product is equal to 1. So let me write immediately the expression for the moduli space with those labels mu1, mu k. So what is it? So these are k tuples of elements of G. Ci sits in the conjugacy class of the exponential of mu I, and their product is equal to the group unit, and it's all divided by G. Okay. Well, so one important question that I want to discuss is a question of dimensions. So what are dimensions of those moduli spaces? Well, of course, it's not always very easy to compute those dimensions, because you see already we are supposed to solve some equations, either this kind of equations or this type of equation in our Lie group, and then we are supposed to divide by the action of G. So this means that here I would only give you a simple computation in the generic case. So this would mean that here, for instance, we assume that the dimension is as if here this product map is at least locally subjective, and the action is more or less free, or maybe there are finite stabilizers. So this means that this will be the dimension for the generic case. In particular, I will give you one exercise to see what happens in non-generic cases. So let's first say this sigma is empty. So now what will be the dimension of M sigma G? Right, first of all, you start with a space G to the power 2G, right? So we have 2G times the dimension of G. Well, now it depends a little bit, right? What's the image? Assume that the map is surjective, as it usually is, and assume that the differential, well, that there are some places where the differential has maximal rank. So then, since you impose a condition that this product is equal to the group unit, so you impose the dimension of G conditions, so you would subtract the dimension of G. And now, if the action here is free or quasi-free, meaning that the stabilizers are discrete, so then you would subtract one more dimension of G. So the formula will give you 2G minus 1 times the dimension of G. Notice that even when it's true, in general, the moduli space is not smooth. So this would be the dimension of the top dimension stratum, or the principal stratum in this stratified space. Right. Well, now perhaps it's a good point to think of an exercise we had. So remember, we had an exercise for today, and we didn't have time to look at it at the exercise session, but I was promised some help with this exercise during the lecture. So there was an exercise of finding sufficiently, or whatever, as many as possible curves on the surface of genus G which would produce Goldman variables or Goldman functions in involution. So let me try to draw a beautiful surface, or at least as beautiful as I can. Now, yeah, so could you help out?
Yes.
Yeah, I was promised some help. So do you, want to have nice colored chalk? So
I was a bit cheating and I checked how many I should find. So actually this dimension count gives us 6G minus 6 for SU2. And we are supposed to find a completely integrable system, so we are supposed to find 3G minus 3 curves which are pairwise disjoint. So basically one can just link these holes first. That will give us G plus 1, and then one can for the last one and the first one cannot put any more curves, but for all the other ones one can actually put 2 more curves on both sides of this picture. So that will give us G minus 2 times 2, and that adds up to 3G minus 3.
okay, thanks a lot. Thanks for your help. Yeah, right. So here we get, using those Goldman variables, 3G minus 3 of them, and they commute. So 3 minus G Goldman functions. In involution. And in fact, there is a paper of Jeffrey and Weizmann who found those curves and who proved that this indeed gives rise to a completely integrable system on the moduli of flat connections for the case of G equal to SU2. You see, in this case, this dimension of the top stratum, so the dimension of M will be 2 times G minus 1 times 3. And, well, this is, exactly equal to 2 times this 3G minus 3. And this means that we get exactly the half of the dimension of commuting variables. You see, one purpose here, we don't really still, even though we have a rather nice description of this space, we don't really understand it so well for 2 reasons. One reason is because we have to solve those nasty equations, and then we have to divide by the group action. So that's why it's welcome to have any concrete functions which would especially have nice properties. Now, a small exercise here. So as I said, this works generically. Now check what happens in the case of G equal 1. The generic dimension formula predicts 0, but this is actually not true. So the situation is not generic, so the dimension is non-zero, and I invite you to find what it is. Now, one more comment about those examples. So, just to link it to what we did in the first class, So again, these dimensions, and again this. So let's look at this example, at the example of the moduli on the sphere. So there is a theorem of Lisa Jeffrey, which says the following. So for mu1, mu k, small enough, well here obviously I don't give you the technical formulation, so for sufficiently small mu's, this moduli space sigma g mu1 mu k, and maybe here instead of sigma I just write a 2-sphere, just to be precise that the genus is 0, is isomorphic as symplectic space to the following. So we consider k-tuples of elements of G, which is identified with G star. We require that xi to be in the coadjoint orbit defined by mu I. You see, I'm now freely mixing G and G star. That's because of this scalar product that I have on the Lie algebra. And I require x1 plus xk to be 0. And I divide by the adjoint action. So if you remember the first class, this is actually the same as the reduced space for the product of coadjoint orbits, O mu1 through O mu k. Okay. And you see, what is interesting, actually I find it quite remarkable. So here we look at solutions of this equation, x1 plus so on plus xk equals 0. So some linear equation, x's in given conjugacy classes add up to 0. And here we look at the at solutions of the equation C1 times C2 times Ck and so on equal to 0, where the conjugacy classes of these guys are fixed. And it turns out that the spaces of solutions for mu's small enough, they're just isomorphic. And they're also isomorphic as symplectic spaces, where here we use the Kirillov-Kosten-Suryo Poisson bracket or Kirillov-2 form, and here we use the Satir-Bott form. See, I think it's an interesting result. Now, just to tell you what goes wrong if mu is getting bigger. Then, of course, imagine you're in a compact group. Then your compact group, if you exponentiate, it ends somewhere, and then you come back, right? It doesn't happen here. Suppose you take very big mu's. So then, when you exponentiate, even here you fall back on the conjugacy classes which correspond to smaller mu's. So there are some more intricate results which tell you what happens for big mu's. But this one I think is already quite interesting. Now, how is it with timing? I have like 1 minute or 10? 5. Oh. I think here you should be kind of more definite. But okay, let's I suggest let's make it shorter rather than longer. So I want to show you one more dimension calculation and give you one problem for tomorrow. So now let's take a particular example here. K equals 3, and G equal to SU2. Now, how those conjugacy classes look like? So SU2 is like a 3-sphere. So here you have a group unit, and here you have the other central element minus the group unit. Now, when SU2 acts on itself by conjugations, it gets foliated into 2 spheres, which go between those 2 central elements. So that's pretty much like the picture of a 2-sphere foliated by the circles, and there are 2 poles. So this means that typical conjugacy classes are 2 spheres. Now let's make the dimension count for this space for the case of k equal to 3. So the dimension of M, so S2, SU2, mu1, mu2, mu3. So at least if the generic dimension count works, it will be dimension of the first conjugacy class plus the dimension of the second one plus the dimension of the third minus dimension of G minus dimension of G. So that's the generic formula. And generically what we get here is 2 plus 2 plus 2 minus 3 minus 3, which is 0. So this moduli space, even generically, is 0-dimensional. So it was originally one of the problems in the problem sets, but then I took it away just to attract your attention to the fact that this is an interesting problem, right? So this moduli space, it can be either empty or non-empty. Either it's a point or there is nothing at all. So, question, when is it non-empty? Now for SU2, you can simply solve it by hand. For the case of SUN, that's already a highly non-trivial problem, and its solution requires some quantum Schubert calculus. So it's a kind of complicated problem to decide when those moduli spaces are empty or non-empty. And that's also one of the aspects of what one can do with moduli spaces. So it tells you about the products of those unitary matrices and when this product can have some given set of eigenvalues. Now, the last thing I want to tell you today is to make one comment and give you a problem to solve for tomorrow. So we constructed a bunch of highly non-trivial symplectic spaces. In general, they are not smooth, but at the moment we are kind of ignoring this fact. So we have spaces M sigma G, eventually with some mu's around, and we claim that they are symplectic. So there is a canonical 2 form coming from the Atiyah-Bott construction. Of course, one question that one can ask is about the cohomology class of this form inside a properly defined H2, let's say, of MR. And the general statement is that whenever this space has a sufficient dimension, that is, it's non-empty and its dimension is bigger than 0, right? Because if it's just one point, then this cohomology class cannot be non-vanishing. So if dimension is bigger than 0. So then, well, one can do many things. So one big story was computing the cohomology ring or intersection pairings in the cohomology ring of those spaces. But one simple question, or one simpler question that one can look at, and that's what we're going to do tomorrow, is try to compute the symplectic volume of M. Here, since in general it's not smooth, perhaps one should say this is a volume of the principal stratum. So we are avoiding those smaller dimensional places. So tomorrow we're going to discuss the formula for it, but as a preparation I would like to give you a problem, and in fact this is a problem 3 on the problem set 2. In fact that's a formula due to Frobenius in H96. So it's a kind of old calculation. So we try to recycle it here. So you see, we are interested in those spaces of homomorphisms from pi 1, which is an infinite group, maybe something like a free group or a group with one relation. And we are mapping it into some, say, compact or maybe non-compact, semi-simple, or some kind of Lie group. But what about the following? What about mapping it into some finite group? Let's say H, or let's say G, is a finite group. So then let's consider the following set. Consider the 2G tuples of elements in G. And, well, let's impose one of the typical conditions that we were imposing before. So the product of commutators BG is equal to Z, and Z will be central in H. Well, now this is just a set. Of course, there is no symplectic form, there is no nothing. This is just a finite set. So what we can do, we can try to compute the size of this set, just the number of elements. And it turns out that there is a beautiful formula for this number. That's the formula you suggested to try to find for tomorrow. So it's a sum over the irreducible representations of the finite group. So let me parameterize them by the corresponding characters. So let me identify the characters with the representations. And, well, just not to make a mistake, there is some constant, which is just the number of elements in the group to the power 2g minus 1. So then there is a character computed at the group unit, which means the dimension. So these are dimensions of those irreducible representations to the power 2g minus 1. So this is just dimension of irrep with character chi, and here the character chi computed on this central element. Yeah, this is a kind of a little bit mysterious formula. So it has in particular those sums with dimensions of irreducible representations in the denominator, but of course here we're supposed to be able to do it just by hand using the standard theory of characters. Now the thing is that it turns out that the volumes of the moduli spaces, they are governed by a very similar formula which is due to Witten. So there will be characters of our group G, there will be dimensions of its irreducible representations, and, well, so we'll see this formula tomorrow and we'll discuss how, well, I'll probably give some sketch of a proof. But it's interesting to compare it to the situation of just a finite group, where a similar formula surprisingly comes up, and it's already known for more than a century. Okay, that's it for today.